All right, in this video, we'll be talking about answering the essential question, how can we describe the force of friction, as sort of we like to in physics, and also set up the lab work for this week. All right, so let's first sort of start with some notation here. So we'll just kind of use the force, capital F, and then we can describe it with a subscript, lowercase f, so the force of friction. If we consider an object, like a block, and we're going to apply a force to it. So remember that one of the types of forces is the applied force, like a push or a pull. So we're going to actually measure that applied force by hooking a device called a spring scale or a Newton meter. So it's got like a little spring in there and it's calibrated so that as we pull it, that stretches the spring out and it moves sort of an arrow that's sort of pointing to how much force there is. And so we can actually measure the force, sort of like our pull, an applied force. We'll call this a force. And again, keeping this notation, it's like an applied force. Okay. As we slide an object across a surface, there's going to be a resistive force. Okay. You've experienced this resistive force in your own life. We call that friction. It's the focus of today's question. So as we slide this block across the lab bench or across a piece of wood or the gym floor or whatever surfaces, friction exists between two surfaces, right? There's going to be this opposing force, and so this is important that it's going in the opposite direction as the force applied, right? If I push this eraser across here, okay, then that's sort of like my applied force. Well, the friction is going to always go in the opposite direction. Okay. And if we think about this in terms of Newton's laws, you say, okay, well, as I push this thing, I set it in motion. Shouldn't that be an object in motion, remaining in motion? Like, why does it come to rest? It's not at rest if I push it. It's an object in motion, but it quickly comes to rest. So we can say the fact that the object comes to rest is not due to the absence of my push force. Like, oh, it's because you stopped pushing it. That's why it comes to rest. You need push force to get things going. That's what human beings thought for a long time. That rest is natural. If you violently disturb something with a force, it wants to come back to rest. But that's not true. Rest is just as natural as motion. Okay? So the fact that the object comes to rest is not due to the absence of my push force. It's due to the presence of some other force. And that force is friction, right? So it comes to rest because there's an outside force acting upon it, friction, all right? So if I pull a block along, and I pull it at constant velocity, and this is an important procedure to adopt for our lab work. If we pull it at constant velocity, let's call like this direction, x, this is the x-axis horizontally. If I pull something along at constant velocity, the sum of the forces in the x direction is going to be equal to mass. The mass times the acceleration in the x direction. The forces are my applied force and this frictional force that acts against it, right? So this is my frictional force. But there are other forces acting on this also, okay? What is the acceleration of something that I pull with constant velocity? How much does it accelerate if it's constant velocity? Exactly, 0, right? Everyone was silent because it's just null, nothing. If something is at constant velocity, it's not changing its velocity, it's not speeding up or slowing down, this is 0. So if the acceleration is 0, because we adopt a procedure to pull this with constant speed, we don't want to pull it, and accelerate it, we have to accelerate it from rest, but once it's moving, just pull it along at constant speed. That ensures the acceleration is 0. That ensures that the forces acting in that direction, your applied force and the friction opposing it, are balanced. They're equal to each other. Now that's going to be helpful because now we can start to describe, we're measuring friction basically. If I could somehow measure how much force it costs me to push this eraser along, what I'm indirectly measuring is how much friction is acting against it, right? Because it's moving at constant velocity. It's a slow velocity. But even a faster, as long as it's constant, okay, friction is opposing my push. And so by measuring my push or my pull, my applied force, I'm really measuring the friction. Okay? So the data table that we're going to collect, we're going to measure some forces. We're going to measure the applied force with our Newton meter, our spring scale. By measuring this, we're really measuring the friction. Okay? What is a force that I said you should always sort of consider first when you're thinking about an object? It always goes in this direction. That's a big clue too. What do we call this force that goes in that direction? So we'll say that this is a physics block, and it has mass. And if it has mass, it has weight for what? I'm asking a question. It doesn't get much funnier than that in physics lab. I'll edit in some applause later, you guys, for YouTube. Wait for what? Wait for what? You guys get it? Weight, correct. Weight equals mg, okay? So it has the force, and we should be consistent, right? So we can call this the force due to gravity, F sub g, and it's in, weight, we call that weight, and weight is mass times the acceleration due to gravity. So we'll be able to measure the mass with like a triple beam balance. How many kilograms of mass do we have? We'll be able to calculate the weight, the force due to gravity. Does anybody remember the name of this force? That sort of, it's keeping you in your seat right now. Like you have mass, you have weight. If you didn't have a force that was pushing up on your weight, you would accelerate towards the center of the earth. And you're not accelerating towards the center of the earth. You're sitting here. And so there must be some up force. It acts perpendicular to the surface. And a math word for perpendicular is normal. It's normal to have a math word for perpendicular. No, the word is normal. Normal means perpendicular. So we call that the normal force. Okay? So this eraser here has mass, it has weight, but it's not accelerating this way. If I remove the normal force, like all the atoms of this metal have electrons on the outside, and there's electrons on the outside of the atoms of this eraser, and they repel each other, and so it doesn't sink through. That's really what the normal force is. It's like an electrostatic repulsion. If I remove that normal force, you can see that indeed the weight of the object makes it accelerate. So when these forces are balanced, you have the same situation here. Zero acceleration, forces are equal. If you remove the normal force, like if you're standing on an airplane, you've got good solid metal, atoms underneath your feet providing a normal force. But the moment you're like, I'm going to step out of this airplane, hopefully with your parachute on, then your weight will accelerate you pretty quickly. Okay. Thank you. So we're going to have the weight equal to the normal force. And that's kind of like over here. The sum of the forces in the y direction will be equal to mass times the acceleration in the y direction. And again, because the object is going to be sort of like at rest on a level surface, the weight equals the normal force. So the acceleration is zero, so the two forces that are acting this way. So here we're considering like applied, the force applied, and the force of friction horizontally. Here we're considering the weight, the force of gravity, and the normal force, F sub n, vertically. And these forces are equal to each other, and these forces are equal to each other. And even though they're equal and opposite, they're not a Newton's third law force pair. We talked about how we sort of qualify that. We need to have two objects for a Newton's third law force pair. It's like the block is interacting with other objects if you wanted to get the force pair. All these forces that we are examining are acting on the block. So like even though this is equal and opposite of this, it's not a Newton's third law force pair. And even though this is opposite of that, it's also not a Newton's third law force pair. They're both acting on the block, so they could. How can we describe the force of gravity? We've yet to do that. Here we go. We're going to describe it with this equation. The force of friction. How can we describe the force of friction? I misspoke a moment ago. Force of gravity. I can't think of it. How can we describe the force of friction? Kind of related to gravity, actually. And it's kind of not obvious why that would be the case. Like, why does something happening in this direction have anything to do with here? We kind of use our reasoning to make sense of it. So this is the letter mu, and it's not an M. I'm not drawing a fancy looking M here. This is a U with a line on this side of it. Okay, or maybe sometimes it's like straight down like that. It's the Greek letter mu. Okay, MU, U. It's the coefficient of friction. And the force of friction is equal to the coefficient of friction mu times the normal force. So like I said, it's, the normal force is equal to the weight, and the normal force has something to do with friction. This is the best we can do kind of theoretically when it comes to friction. Friction is poorly understood. The best that we kind of, can make sense of it is just like I mentioned, like there's atoms with electrons, they kind of repel each other. That's what provides the normal force. And the surfaces, even seemingly smooth surfaces, have little bumps and divots and sort of irregularities so that, as I slide these things past each other, the atoms that are sort of, rubbing against each other, there's like, it's catching different places. Imagine like if I put a piece of Velcro and another piece of Velcro and try to slide that across, how much friction there would be, because there's all those hooks and, things like that. But Velcro is designed that way. But if you zoomed in sort of at a microscopic level, you'd find that every surface is kind of like that, kind of Velcro-ish, that has these, bumps and divots and things like that. And that's kind of the best we can do to say, oh, well, that's why there's friction, that the surfaces are kind of catching other parts of it. And so it kind of makes sense because like empirically or just, sort of like from experience, from our tacit knowledge, we know like sandpaper, very rough, right? It's going to have a lot of friction. Like if we were to run, move this block against a sandpaper surface, there'd be more friction than if it were like ice, which has very low friction. Like ice skaters will know that, or maybe they won't know, but you're basically gliding on a thin layer of water. Like the ice blade melts a little bit of the ice, and so it makes like a lubricated like water layer that basically no friction, or very, very low friction. So this coefficient is a true coefficient. It's a ratio of these forces. We can divide each side by the normal force and realize that the coefficient of friction is a ratio of friction to the normal force. This will be the conclusion for your lab work. You will tell me the coefficient of friction between two surfaces that we test. And so let's go ahead and sort of spell this out. The coefficient of friction. It's specific to the surfaces. Between two surfaces. So you have to report the surfaces that you're testing. All right? Like the coefficient of friction between a wooden block and a tile floor. Okay, if we're going to do the lab on the floor. The coefficient of friction between Air Jordans and a basketball court. Okay? And you can kind of see with that example why like this is important for engineers, for material scientists that are like, yeah, I need to make a really good skateboarding shoe. What's the physics, of like how does a skateboarder interact with their, the grip tape, has a lot of friction on it, right? So different sort of coefficients of friction for different purposes. Sometimes we want non-stick coating on our cookware, right? We don't want our eggs stuck to the pan like every time I cook breakfast. Like, okay, have a really low coefficient of friction, like Teflon, with very, very low coefficient of friction. The synovial joints and your elbows and knees, okay, incredibly low coefficients of friction because the wear and tear of like motion throughout a lifetime would cause, it already does cause this, but that's, when you measure it, it's a really, really low coefficient of friction, okay, but it's specific to the surfaces. Let's think about the data that we'll collect in order to be able to reach this claim. So remember, claim evidence reasoning. The claim that you're going to report to me is, I claim that the coefficient of friction is this number. It will be a number. And I measured wood and tile. I measured rubber tennis shoe and lab bench, whatever the surfaces are that you happen to test. And it's probably going to be, I will decide what surfaces we'll test. I'll do the lab and you all will watch me do it. That tends to be the way lab work has gone this year. But I don't know, maybe we'll have enough apparatus we can bring it out and still keep everybody, sort of separate using their own apparatus. And it was the only physics, section I have this semester, so it's not like I have to share it with like another class coming in. So, maybe we'll let everybody collect their own data. All right, let's talk about the data table. Remember, we've got this procedure we've adopted where the applied force is being pulled just so that there's constant velocity, so that the applied force equals the frictional force. Like, that's really important because we're measuring this directly with a spring scale, and we're saying, well, it's got to be equal to the friction force, again, for the reason I explained with Newton's laws of motion. This does not come to rest due to the absence of my push force, but rather due to the presence of the frictional force. And so if I could measure the strength with which I push or pull, I'm indirectly measuring the friction that's opposing that motion. That's sort of the thinking that goes into this procedure. So for a data table now, we'll have the mass of the thing, okay, that we're pulling. It'll be measuring kilograms. If we know the mass, we could calculate the force due to gravity. That will be in newtons, right? So that's going to be its weight. So that's just saying, hey, whatever mass that I have here, and this is going to be the thing we vary. So we are going to have 7 data points. I'll tell you the first one we'll start with will be 1.25 kilograms. Okay, and tomorrow's lab day, so we can say, how are we going to get the force due to gravity? If I'm telling you I'm about to pull a 1.25 kilogram block across a lab bench, and I say, what's the force of gravity acting on this? How much weight does my 1.25 kilogram mass have? The physics students will say, I'm waiting for you guys to answer. I'm not just thinking right now. What's the thing? I'm waiting for you guys to answer. Physics students will say, you're not physics students, guys. I already went through all this. It's your job now. 1.25 kilograms, that's the mass. How do we calculate the weight, force due to gravity? You multiply this number by this letter. 1.25 G. Oh, come on. What's G? Who's got it? The owners? Did you type it in the chat? $12.26, and I've already got the units taken care of right there for you. I'm sure that's right. That seems reasonable. 12. Anybody else solving that out there, getting the same thing? 12.26. So how did they get that? G, remember, as what value? What value should we use in this class for G, the acceleration due to gravity? 9.81. So this times 9.81 is hopefully that. I haven't checked it myself, but I trust that 2 students doing it, getting the same answer, they probably didn't make the same mistake. So like, we're going to vary this. We're going to add mass to it. I'm going to pull a 1.25 kilogram block, and if it's got 12.26 newtons of weight, how much normal force is there? Keeping in mind that in the y direction, the weight, the force due to gravity, like it's not accelerating in this direction, right? Like I'm going to put a block on the table, and unless it's an awful lot of mass and a lot of weight, it's probably true, just like as this eraser sits here, like this has weight, but it's not enough to like compromise the structural integrity of this metal. Like I'm not going to put so much mass on the table that like the table will break. But if it did, then this physics doesn't go away. Like it will accelerate in the direction where there's a net force. No longer does the table provide normal force underneath it. It's going to accelerate down. So, you know, as long as the atoms are strong enough, the table, the surface will provide whatever normal force is needed to keep the thing, you know, stationary. That's not like unlimited. There is a mass that would actually break the atom, you know, the molecular bonds of the table. But we're not going to put that much weight on the table, right? This is public property. We're all taxpayers. We don't want to destroy public property by overwhelming the structural integrity of our lab benches. So if the force of gravity is 12.26 down and it's not accelerating, right? The acceleration is 0, then that must mean that this equals that. The downs equal to ups, right? So if I have 12.26 down, then I could say my normal force, also in newtons, is going to be also 12.26, right? Like this, these two numbers will always be the same. The applied force in newtons. Now this is going to be the thing that's we're actually going to measure with this device called a Newton meter. It measures newtons of force. It's a spring scale, okay? It's going to be calibrated to newtons. So when we actually pull the object, like we push it, we pull it along, we can read off how much pull force. So this is our applied, our pull force. And provided we adopt that procedure of apply a force such that it accelerates 0, it's moving with constant velocity. Now, when you disturb it, just like now it's at rest, and now it's moving some non-zero speed, right? So I do accelerate it initially. There's no way around that. It does accelerate, but as soon as it starts moving, then just move it at constant velocity. It can be a slow speed, it can be a fast speed, but it needs to be constant, so you're not accelerating. Then your applied force, whatever it is, will be equal to the thing that's the source of today's question, the force of friction, right? What we're really doing is we're just pulling it just fast enough to see what friction is doing against it. Like, oh, this is how much I need to pull it so that friction just sort of stops it. How much friction is there? You're really reading off the friction by doing this. Yes, it's how strongly you're pulling it, but you're pulling it just strong enough to overcome the friction that's acting against it. So by pulling it at constant velocity, the acceleration in the x direction is 0. So the right's equal to left. Okay, the applied force equals the frictional force. And so the frictional force in newtons will be the same thing as the applied force. These numbers will be the same in your data table. If you want to know the coefficient of friction, that's your claim you're going to sort of reach here. Then your graph is going to look like, yellow, oh no, sour lemon chalk. That's our scalar chalk. We need an S. Your graph here, we're going to plot the frictional force, which is like these numbers, against the normal force. These are measured in newtons, right? So these numbers, you already know your first coordinate, 12.26. I don't know how much pull force it takes to move that, but we'll figure it out tomorrow. So you're going to plot these numbers on the y-axis against these numbers on the x-axis. You will find what your intuition may suggest to you. If you put a bunch of mass on top of a block, like I'm going to put some weights on this thing, right? Because mass has weight, like we talked about. Don't you think it's going to be harder to pull that along? Like if you just have a big, massive collection of, blocks. To pull that costs more force than a little bit of mass. It's like intuitively we know that that's true. And it really kind of shows us like why there's some validity to this equation. Like the more weight, the more normal force, the higher this number is. This is just specific to the surfaces. It's just a number based on like ice and, Teflon, really low, really smooth, really slick. Gonna have a low coefficient. So it's really saying like the weight has something to do with the frictional force. Multiply the weight by this number, and that tells you how much friction will be against it. That's sort of what the theory is. So you'll find that as we add weight, we increase the normal force, there will be more friction. You'll find a trend here. Okay, like as we increase the weight, the normal force, the frictional force goes up with it. You'll be able to draw a trend line, a single line representing the trend in the data. And as usual, find 2 points that are not data points. You can calculate the slope. If you take a look at this equation and think about it like the equation of a line, y equals mx, then by plotting the normal force on the x-axis against the frictional force on the y-axis, the slope of our best fit line will be the coefficient of friction. All right? So it's not like the pendulum lab where you take the slope and you set it equal to 4 pi squared over g. It's not like the drop lab where you take the slope and you set it equal to 1/2 g, solve for g. This one, the slope is your claim. Like the slope will be your coefficient of friction. What are the units of mu? None, right? Because the rise over the run, newtons of rise over newtons of run, it's a ratio of forces. So it is that's why it's called the coefficient of friction. It's just a number. The higher the number is, the rougher the surfaces are. So you have a coefficient of friction, like let's just put some values in here. If the coefficient of friction is 2, that's really high. Coefficient of friction 2 is a pretty high coefficient. That's like saying it's going to cost me twice as much force to pull this thing than it even weighs. Like imagine something that weighs 10 pounds, but I got to pull it with 20 pounds of force. Why? Because the surfaces are so rough. Because I put it on like spikes and Velcro and sandpaper. See what I'm saying? Like then you got a really high coefficient of friction, then the heavier it is, the more force you got to pull. Okay. So it's just a number. If it's a number that's like I mentioned, Teflon. Like Teflon's like 0.004. Teflon on Teflon. Then it's like basically saying, even though it might have weight, multiply it by a number that's basically 0, hardly any friction at all. Nice, my eggs aren't going to stick to my non-stick surfaces. Okay. And so that's a little bit about how we describe friction. Like this is the equation for friction. It doesn't, we can't do much better than this, unfortunately. There's not an extensive theory about friction. It kind of shows you how poorly understood it is, how we got a lot more work to do with really like theoretically understanding friction. There's no way I could say, give me any two surfaces, and I'm brilliant enough, I will calculate theoretically what this number is, like by understanding the properties of like the metal or the wood or whatever it is. There's no theory like that exists. In order to determine the coefficient of friction, you must do an experiment like we're going to do tomorrow. Like it has to be determined empirically. There is no theory anyone's ever come up with that can like, basketball court? Okay, let me calculate what it would be for a basketball court and a basketball shoe. That doesn't exist. You have to take a basketball shoe, you got to take a basketball court, you got to do this experiment to determine it. And you could look up right now, if you wanted to, a table of different coefficients of friction for surfaces that have been tested. Like I could, consult the literature and I could show you that like important surfaces have been tested. Engineers want to know what's the coefficient of friction for like wet asphalt and rubber or dry asphalt and rubber. Why would it be important to know the difference between those coefficients of friction? Because if it rains and the asphalt surface gets slick, or if it gets wet, is it going to be more slick, with rubber tires? And so questions like this where friction sort of really matters. You want enough friction that your wheels can grip the road, right? They're not sort of skidding out. But not so much friction like you have to sort of fight against it. So this is important. It's something that we deal with all the time. It's why it was difficult to realize Newton's first law of motion. There are all these outside forces that act upon objects that tend to sort of slow them down and stop them, like friction, like gravity. Right? So objects remain in motion in a straight line, constant velocity, until outside forces act upon them. So when I disturb this, it doesn't stay in motion forever and ever like it should according to the first law, because the surfaces rub against each other. There's this outside force acting upon it. Okay? So tomorrow we'll add more weight to our block. We'll start with this one, right? We already know the weight. We'll pull it, we'll fill in this, and then we'll just keep on adding kilograms of mass and therefore weight. And we should find that it costs, more and more friction the heavier it is. Kind of think about it like, as we add mass to it, we're squishing the surfaces together more. So all those little bumps and divots, that's like the source of the friction. Now they're like squeezing together even tighter. So yeah, it kind of makes sense why there would be more friction as we like pile weight up on top of this block, right? It's going to be harder and harder to pull. We should find that true, quantify that tomorrow. Claim. Coefficient of friction is some number, no units, right? The units cancel because newtons over newtons. It's a ratio of these forces. Evidence, see graph, right? You're gonna generate a graph with this week's data. Reasoning, because theory suggests the force of friction equals mu times the normal force, I can determine the coefficient of friction by plotting a graph of this, or by varying the weight of the object and then pulling it. You kind of just re-describe the procedure, how we sort of got to our answer, right? So always a claim, evidence, reasoning when I tell you that that's what I'm expecting for the lab work. And typically, bless you, you will have to do that for lab work. Like last week we did kind of just like a practice calculation kind of thing. This week it will require you to plot data, reach a numerical answer, report that as your claim. The evidence is your graph. The reasoning is based on this theory here. All right. So feel free to pause and replay this as many times as you need to make better sense of the lab work. And we'll see you next time.